Section 4.4 The temperature dependence of reaction enthalpies. Usually, the enthalpy of formation for chemicals are provided at the room temperature and the room temperature only, because it's too tedious to include the enthalpy of formation of all other temperatures. So, how can we determine the reaction enthalpy at a temperature different from 25 degrees Celsius, the room temperature? Well, for any given chemical, we learned that the enthalpy at temperature T is equal to the enthalpy at the room temperature plus a correction. What correction? The integral of Cp dt. Well, this is because delta H over delta T is equal to Cp under the constant pressure condition. Pay attention to this T prime here. It's just a dummy variable. I used T prime only because I used the T as the upper limit here. Therefore, I need to use a different variable. So I'm using T prime, but you can use X to replace T prime. This Cp of T prime is to tell us sometimes the heat capacity depends on temperature. Now, the reaction enthalpy is often given in joule or kilojoule per mole reaction, and thus what we usually do is we have the enthalpy of the reaction at temperature T is equal to the enthalpy of reaction at the room temperature plus the correction. The correction is the integral of delta Cpm per mole reaction, so Cpm dt. So what is delta Cpm? That's simply the Cpm of the products minus the Cpm of the reactants. And very often, Cpm is independent of temperature within a small temperature range. And then we can simply take this delta Cpm out of the integral. How do we understand this equation? It looks complicated. This is the enthalpy of reaction at the room temperature. This is the enthalpy of reaction at a different temperature. Why do they differ by this much? Why do we need to take the difference between the Cpm of the products and the Cpm of reactants? Well, here it is. When we look at the enthalpy of reaction, for example, for this from A to B reaction at a temperature T, we can divide this reaction into 3 steps. The first step, we convert this A at temperature T to A at the room temperature. And then we do this reaction at the room temperature. The reason is this information is often available. And then we change the temperature of B from the room temperature to temperature T, the target temperature. So again, if you look at the 3-step process, the initial state is A at temperature T. The final state is B at temperature T. Therefore, the change of the enthalpy of this entire 3-step process is simply the enthalpy change of this 1-step process at the same temperature T. The reason is simple. Enthalpy is a state function. And then what we need to do is we need to compute the enthalpy change of step 1, step 2, and step 3. And then we sum it up. Step 1, step 2, and step 3. In step 1, it's just the integral of Cp dt. And it's going to be from temperature T to the room temperature. However, for convenience, I'm going to swap the lower and upper limits. And by putting a negative sign in front of the integral. Again, if you swap the lower and upper limits of integral, you need to put one additional negative sign over there. And then step 2. That's simply the enthalpy of the reaction at the room temperature. Step 3, we're going to change the temperature from the room temperature to the target temperature. And we need to include the Cp of B inside this integral. Now, what we can do is very simple. We combine all the terms, and then you can see this integral and this integral can be easily combined by have this Cp of B minus Cp of A together. So in the end, we have this enthalpy of reaction at temperature T is equal to the enthalpy of reaction at the room temperature plus this correction. This correction has a baseline, room temperature. So we go from the room temperature to our target temperature T. And we need to integrate this delta CPM. I forgot to put molar here and molar here. Oh. Okay. Now let's look at one example. This reaction, we have 2A plus B. The product is C plus 3D. And then we're going to divide this into 3 steps. Step 1, we change the temperature. Step 2, we allow the reaction to proceed at the room temperature. Step 3, we change the product's temperature to T. Alright, so again, we'll see the enthalpy of reaction at temperature T minus the enthalpy of reaction at the room temperature is simply the integral of delta CPM. Delta CPM is the CPM of the products 1C and 3D minus the CPM of the reactants. We have 2A and 1B. Now a numerical example. Let's say the enthalpy of reaction of this 2A to B from 2A to B is negative 200 kJ per mole at the room temperature. And now let's calculate its enthalpy of reaction at 398 K. All right, so this is 125 degrees Celsius. So how can we do this? First, we need to know the CPM of A and B. Let's say CPM of A is 25 joule per mole K. CPB is 40 joule per mole K. Pay attention to the unit. Over here, this is joule, and for reaction enthalpy, usually it's in kilojoule per mole. So remember to do the conversion. So delta CPM is simply 40 minus 2 times 25 because of the coefficient in front of A. There are 2 of A. So it's going from 2 times 25 to 40. The change is negative 10. Now let's look at the enthalpy of reaction at temperature T. We just need to have the reference here. This is our reference. This is our baseline. Our baseline is negative 200 kJ per mole plus the correction from the room temperature to the target temperature. In this case, it's 398. And then delta CPM is negative 10. We just do the calculation over here. You're going to have negative 10 times 100K. All right, that's just negative 1,000 joule per mole. So this is 1,000 joule per mole. However, this reaction enthalpy is in kilojoule per mole, so we need to pay attention to the conversion. Together, it's going to be negative 201 kilojoule per mole. This example tells you how to compute the enthalpy of reaction at a different temperature, other than the room temperature. Also, it reminds you, even if the target temperature differs moderately or even significantly from the room temperature, I would say the enthalpy of reaction at that temperature is very close to the enthalpy of reaction at the room temperature. So these two are very close, only because this correction, the integral of delta CPM, is usually small. And why is that? First, delta CPM itself is small. Why? Because it's the CPM of the reactant products minus the CPM of the reactants. So mostly they cancel. All right? Even if they don't completely cancel, you'll get a very small delta CPM. And then when you integrate this delta CPM, the result is very small. In this case, it's only 1 kilojoule per mole. The correction, the difference between the room temperature and the target temperature, is only 1 kilojoule per mole, despite the 100K temperature difference. All right, if you compare 1 with 200, you'll see we can often assume the enthalpy of reaction is roughly a constant within a moderate temperature range. All right. So even if in some rare cases delta CPM is a little larger, but then if the temperature range is small, let's say only 20K, 30K, still we can say the enthalpy of reaction remains approximately constant within that moderate temperature range. If we look at water, the vaporization of water, it's going from liquid water to gas water. The liquid water and gaseous water have different CPM. However, the difference is not that significant. And that's why the enthalpy of vaporization of water at 100 degrees Celsius is very close to that at the room temperature. So it's 41 versus 43. So why the difference? There's a 2 kilojoule per mole difference. That's actually the integral of delta CPM from the room temperature to 100 degrees Celsius. And that delta CPM is simply the CPM of the gaseous water, the water vapor, minus the CPM of liquid water.